Yeah, we've my wife and I are working on this book, and it's really fun to go back and try to dig up like the original letters between a lot of these guys. We're trying to figure out the how physics lost material mediators and electromagnetism and gravity and stuff like that. But it's so crazy reading these original letters. It was just a very different culture than the one that we have today. Um, it was so much more exploratory, and yeah, I don't know. People are much more defensive today in the intellectual climate of exchanging ideas. But yeah, Darwin also never he was sitting on his treatise for decades at the end of his life, and I think the only reason he even ended up publishing The Origin of Species was because he realized Wallace was about to publish the same idea, and so he actually reached out to Wallace and was like, "Hey man, you want to just publish something together because this is crazy," and because it was completely heretical. I mean, having revolutionary ideas is not always a party is the problem. Like I know at least one or two. I know a couple of people who have genuine revolutionary ideas, and it's been a terribly painful career for them because oftentimes everybody thinks you're a moron until they think you're a genius. That's more often the case than not.
What's that like? It was in the reading. I think it's like Reiki, or I don't know how you pronounce it.
Yeah,
And he
Taiko.
would give all of his research to Kepler because he wanted him to solve or figure it out before he did it.
Oh, is that what he said?
Yeah.
That's interesting. Yeah, there's a lot of apocryphal stuff around that Brahe Kepler. We're going to talk about that actually probably on Tuesday. I'm going to go through that story a little bit more. But it's kind of weird, yeah, because Kepler kind of writes about him like he was sort of a drunk who just wanted to party, but he had like the best uh, observational catalog in the whole of Europe.
So his observation.
Yeah,
Wouldn't Michael get access to all of them before he died?
I don't think he died, but he made him hang out for a while at his palace there. And Kepler was this very like studious kind of nerdy type, and he wanted nothing to do with these big bashes that were going on every night, and he was just kind of like patiently like, dude, can I look at your notes, please? It's wild, yeah. I mean, that's the fun part about everything that we're doing. That's, I think, what is interesting, at least to me, that I want to share with you guys. There is like a whole human element to all of this. It's not like science just emerges as a sea of facts. Like you don't just do an experiment and then the whole world just drops everything it's doing to jump on your bandwagon. And my goodness, it can be very, very hard to bring some of those ideas into play, despite how good they might be. There's a huge amount of momentum in the world of ideas. People really like the ideas that they start out with. They don't want to turn their backs on them necessarily. All right, let's formally get this going. Sorry, a little bit of a late start. We were just talking. Anyways, I want to make sure I give you guys. Let me see. Do we have any business questions, concerns about? I don't know. Uh, any of the assignments bothering you guys? Anything crazy, broken stuff? No. All right, that's good. Um, make sure. All right. Well, let's get some recap on where we left off, and we will just pick up the party. Uh, again, we are going to get. I mentioned this before class started, but we're going to get a little out of phase with what's happening in the textbook and in the workshop. That's okay. So we're going to lag behind here because this part needs built out more than we have time for in the textbook, and some of the stuff at the end is probably not as important as we start looking at basically some of the further we get away from the sun after we start this tour through the solar system, really the less we know about what's going on. So when we start to move out into the gas giants and beyond that, it's very, very difficult. I mean, it takes us years to get a satellite out to one of these gas giants, right? And beyond that, it becomes very, very difficult to study these things. So we have much more to say about things closer to the beginning of our story than towards the end of the story. So I'm going to go at the appropriate pace, which doesn't completely map onto the textbook. So I hope that doesn't disturb anybody. All right. There's still some of you on my list here I haven't heard from, and I would love to hear from you guys. So if you didn't get a chance to talk last class. Uh, say hi today so I can mark you down for being here and thinking. But does anybody want to kick us off with, yes, what's your name? Tuesday. Hey, Tuesday, we've been emailing. We've been emailing a little bit. Yeah. How are you doing?
So I wasn't here on Tuesday, but from what I watched, it was interesting to learn that I feel like I've heard a lot from my math professors that math is a language. And I think it's interesting that in order to understand what's happening in math and in physics, we have to have context behind it and some storytelling. And I never thought of it that way because when I think of it, math really isn't a language because we can't just understand um, numbers and figures without having context or story behind it. So
Yeah. Yeah, it's a pretty heretical perspective, but I think it's true. I mean, it can't be thought of as anything other than quantitative adverbs, right? They're always just modifying some quantities, and good luck making a sentence out of quantitative adverbs. That doesn't mean that it's not powerful, right? I want to be really clear, like all of these weird little pieces of the puzzle that I keep throwing in your guys' lap, I don't want to come across as cynical in any way, and please stop me if I seem that way to you, because that's not what I'm trying to say at all. I just think that there's some interesting blind spots. We inherit these kind of weird wisdoms along the way and just, oh, that makes sense, math's a language. And it's like, well, not only is it probably not a language, it's just like if we as a society get accustomed to thinking about it that way, we might end up with some pretty bizarre conclusions about things, right? Because we might think that the work is done when we have a really nice equation to describe things. And hopefully the Copernican Ptolemaic comparison was a reasonable printout of that. But we'll examine some other situations where some pretty wacky conclusions have been drawn about really, really good mathematics. As we get into relativity, we're going to get into, that might be more next semester. What will we do in this class? I think we'll do some quantum physics a little bit when we talk about what light is. Again, some pretty wacky conclusions that are really completely unjustified, but they're just result from the void where the math is the sufficient endpoint for a lot of the studies. So it's not just an empty glove in the face of mathematics. I think it actually matters, and we'll see more of that as we go along. Yeah.
I actually have a question, and honestly, it might have answered in the beginning, and I might have just missed this part. But so if like the sun is one of the foci for like the ellipses that all the planets are like orbiting, what
Very
what
close.
is
Yeah.
the other part? Like why is it an ellipse then rather than just a circle? Like what is pulling them the other way? Because at first I was just thinking like, oh, the gravitational forces between the planets, but that wouldn't make sense because they're all moving around the sun anyway. So it would be like get all kind of out of whack.
Yeah, you can kind of think of it as, well, you're really talking about averaging out all of the mass, let's say the material in the solar system. And a non-significant portion of it is in Jupiter too. It's not a lot. It's pretty small compared to the sun, but it's enough that the gravitational center between Jupiter and the sun actually is like slightly outside the sun, right? So they're both kind of orbiting a point. Really, bodies orbit each other. We'll deal a little bit with orbit, and yeah, I think we'll get to that. Not today, but very soon we'll talk a little bit more about that and try to build out a better conception of gravity itself. Um, and that's going to be a fun point because, again, the mathematical representation of gravity has gotten increasingly precise, particularly in the 20th century with the Einstein relativity stuff. Super precise, but completely devoid of mechanism, right? Like, why are you sticking to the ground right now? Materially, like, what's holding you to the ground? Well, something is. And what is the structure of what's holding you, and how's that working out? And I think that there's some really interesting revelations to be had there in that domain. And so the more we start thinking about gravity as a tension between bodies, some sort of actual like physical tension between them, they are in fact somehow intermeshed with one another, then the orbital stuff starts to make a lot more sense because it's a little bit like tetherball at the end of the day. So yeah, we'll get into depth with that. What else, guys? What else are we talking about? Anything stick out? I'm gonna call on some people because I haven't heard from you, and I don't even know if you're in my class anymore. Yes.
So last week,
Tell me your name.
or not last week, but Jared.
Jared. Okay. Yep.
Last class we spoke about when scientists are like wrong or right. What would scientists do if they weren't necessarily wrong or right, but the sense that we keep making telescopes that can see deeper into space, looking for the embers of the Big Bang? But if it just kept going, how would they know if there's not? And
Yeah, it might be an unanswerable question. I mean, you can always look at it one way or the other. I think you can always retune your assumptions and just say, well, you know, there was a beginning to this thing, but we just haven't seen it yet, and maybe we'll see it when we build the next telescope. Um,
will there like ever be a point they just stop building telescopes? Like it's like in 1,000 years if they still don't find it.
I don't think so. Yeah, I don't think so. Uh, I hope not. I mean, the other stuff they've been getting out of this new telescope has been really, really incredible. Just in terms of the resolution, they've made some wild discoveries that are going to matter to us a lot very soon, which is like free floating planets orbiting one another with no suns involved. That's pretty far out. I don't think anybody expected that. And that actually might materially matter more to the story that we tell about our solar system than whether the Big Bang happened or not. Um, yeah, I don't know. The Big Bang's a weird thing. It's almost outside of science. Like it almost doesn't. The only reason it even matters to me is that it constrains the timelines by which we're able to tell stories about the things perhaps in our own solar system. Um, the constraint that's been placed upon the stories for our solar system. This might be worth pointing out. Um, you know, Originally, it was like a few billion years to make everything, right? So you didn't have time to like have planets living in different solar systems. You didn't have time for multiple generations of stars. Now that's been walked back on a little bit, but it's still really, really short. I mean, it seems like 13.8 billion years is a long time, but if this, life is thought to have appeared on Earth, maybe 3 billion years ago or something, it's not that long actually. And so you're in a big rush to make everything happen. And the stories you tell are just, perhaps artificially limited. If you have trillions of years to make a moon look the way that it does, well, maybe it makes a lot more sense actually. Uh, but and so the Big Bang narrative constrains things, I think, and that's perhaps the most problematic thing. Not whether or not there was a beginning to the universe. It just doesn't really seem to matter much from a scientific standpoint. Um, I have a hard time imagining it, but other people don't, and that's totally fine. Other people have a hard time imagining there not being a beginning to the universe, and I just don't think it really matters appreciably. So, yeah, no silly questions.
Further space, let's see, other uh, objects and bodies. Does that mean the universe itself is moving and not just like our solar system?
Oh yeah, everything's moving. Actually, the sun's orbiting too. I want to pull. I got a little video and animation of our sun moving. So our sun's orbiting the galaxy actually. So hold on to that thought. Yeah, everything is dynamic. Everything's in motion, and like you pointed out after class, it's a little bit disturbing because the things that we see that are far away, they happened a long time ago. And so what's happening over there right now? I don't know. Nobody knows. Maybe, maybe the universe has ended over there. Maybe it's fantastic, but nobody knows, right? We're limited by this perception of light. And light's actually really, really slow. I'm going to show you guys an animation here in a second. It is unbelievable. Like if on the scale of the size of something like the universe, it is really hilarious how slow light travels. Yeah.
If you've ever heard the phrase "the only constant in the universe is change," that applies to motion.
Yeah, yeah, it's kind of true. Yeah, everything changes. That's a hard reality to face sometimes.
Uh, you mentioned that you don't think that Big Bang being it having it be just a marker for the beginning of the universe is sort of the most important aspect of it, rather than it just being eternal. But I think isn't there also some exploration now that Big Bang is a mechanism by which universes are created, in that it's it's uh, it's an interval. We're in like a period of universe expansion, and then but it's there's a point that uh, having a hard time describing this but there have been multiple.
Like it's a cycle of some sort. Yeah. Maybe. It very well may be. Yeah. But yeah, and that's kind of a different kind of eternity in a way. And then you have this extensive cyclic thing. Yeah, maybe. I actually, yeah, I guess what I'm saying is that to me, it doesn't so much matter whether there's a beginning or not, or it's cyclic or whatever. It's more just how much time do we have to explain the things around us? And I'm very disturbed personally after all these years how the timeline keeps expanding indefinitely with our level of technology. And so for me, like the less interesting question is whether there's a beginning or not. The more interesting question is like, if this Big Bang thing keeps failing every test that we throw at it, why are we constraining our theories based on it? So that's all. I mean, there may be, yeah, it just does, the other parts just don't impact my ability to conceive of the stories about our bodies and our solar system, things like this, like where, how long does life take to evolve? Like, how does these processes happen? Those are more constrained by this preposterously short 13 billion year timeline that we have on it, which just seems unfair to me just because it's changed by, a factor of 3 to 4 in the last 50, 60 years. Probably changed by another factor of 3 to 4, but that impacts everything about the stories that we tell, as far as I can see, for our solar system and for our planet that we're standing on, right? I forget whether I pointed this out already, but like this is the most dense body in the solar system that we're standing on right now. That's pretty crazy, actually, if you think about it, especially if we haven't gotten to how the solar system formed. We'll do it. But if the story is that the whole thing kind of congealed out of this swirling ball of dust and gas, it's pretty wacky that the densest thing wouldn't end up in the center. That's pretty bizarre. And so, but of course that's the toolkit that you have to tell if you only have a few billion years to make all this stuff happen. You're really, really limited in the stories that you can tell about these things. And that's the problematic side. That's why cosmology kind of is in my crosshairs. It's also, again, I know you said you weren't sure if you'd be around next semester, but it's in my estimation, I'll make the case that it rests on really two pieces of evidence with rather elastic interpretations that, yeah, I just don't know that it warrants having the keys to the castle that it does right now. Yeah, I'll get to you in a second.
Two things.
Yes.
I do want to correct you. Earth cannot be the densest thing in the solar system. That would be the sun.
Nope.
That's just not.
It is true.
There's no.
Somebody go Wikipedia it or something, or Google it. It's true. The sun has in theory, the sun has a very dense core to it. But in terms of the body, right? I'm talking about the average density of the Earth is much higher than the sun. The sun's average density is almost about the same as water, actually. It's around 1 grams per cubic centimeter. The Earth is about 5.
Yeah.
So.
The surface of the sun's plasma. Yes.
We'll deal with that word too eventually in due time.
Densest part of the solar system did end up in that sun, that being the core of the sun. Because at the core of every solar system, when a sun dies, right, its core, the dense core is what remains. And that continues to be the center that pulls things around it because it's dense. And that just continues to happen. It explodes.
The core of the sun is denser than the Earth, in theory. No one's ever been there. The point I'm making is that the Earth is the densest body in the solar system. So the sun is a body, and the Earth is a body, and the Earth is denser than the sun. Yeah.
I just googled that and said the Earth is the densest.
It is. It is indeed.
What I was gonna say is I don't actually have a question. It's just like kind of a thought. We were talking about like what is like the most interesting thing to you about like the expansion of the universe and all that. And I would argue that like for me personally, I always like find myself like naturally more interested in like the solar system than like the broader like universe because it's just like what we understand more. I don't know if that makes sense, but like I was having this conversation with like my friend last night, kind of about this, and I was just like talking about to him like I think like as a kid I would always find myself like googling more like stuff about like the solar system and like the moons of Jupiter and stuff like that, stuff that was really interesting to me, or like the rings of Saturn was really interesting to me. and like rather than like these like broad concepts about like the expansion of like the universe. Does that make sense?
Absolutely. I'm right there with you. I also just think that they're more reliable conclusions you can draw about the things that are in the room with you than something that's literally straining the technological ability. You know, like, who knows how light behaves over 14 billion light years of travel path? Like, crazy stuff, probably. And then you try to make conclusions based on that, and it's like, yeah, they're just bound to be less robust conclusions, I think. That just, you might get lucky, but it seems like if you look around the room and try to explain the things, at least the things close to you, using the processes that you can understand here on Earth, then you get a lot closer, I think, to understanding stuff. So I'm with you, yeah.
So it like I understand how like we look out and we see further things, it means that like the whole universe has to be older. But does that mean that like our solar system has to be that same age?
No, 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 no. Well, dating the solar system is a real interesting trick, actually. I'll probably save the details of that for when we start talking about the Earth, because we'll spend a section on Earth as it is one of the planets that we know the best. Um, yeah, dating is actually quite tricky, and in some sense, you know, the dates that we find are the dates that we ascribe to the oldest rocks that we can find. The problem is when it comes to dating rocks, the way that you date rocks is you basically say the last time they were melted. And so, you can look around and say, well, the oldest rocks we found are 4 billion years old or something like that. Does it mean that they're not older than 4 billion years? It really doesn't. It just means that they got cooked and incorporated fresh radioactive elements into them 4 billion years ago. So it's tricky, Again, the timelines that we're all comfortable with, at least from a textbook side of things, they're really conservative, and a lot of them were proposed in an era before we could see as far back as we could see now. And a lot of, yeah, a lot. I mean, this story for how the solar system was formed it was created by Kant and Laplace back in the 1700s. It's basically the same story, this nebular collapse thing. It's a really old idea that people have inherited for a really long time, and they've been kind of, propping it up. But there's huge problems with the formation stuff, and I think those mysteries are really fascinating. The reason I bring up, you know, the density thing with Earth that's really, really fascinating is just that it's very, very difficult to even mathematically explain how you get little pebbles to stick together. So you can get a bunch of dust to group together into a pebble pretty easily, like because dust has, electrostatic forces that'll hold it together, and it doesn't have a lot of mass, so they don't really collide very hard. Once you get pebbles, the pebbles tend to just bounce off each other. So there's this huge problem in planetary science when it comes to accreting planets, which is we don't really know how it goes from being pebbles to being boulders. But once we have boulders, we can make a planet. But how the heck do you get from a pebble to a boulder? And so there's all these little pieces of the puzzle. I'm not like purporting that I have the solution. And I'll throw some wacky theories at you guys as we go. But there's obvious mysteries which abound. And changing the timelines may or may not help you provide a theory for what happened, but it certainly opens the possibilities a bit longer. Yeah, I mean, just imagine for a second if all of a sudden, instead of having 14 billion years to do everything that we see, you have 14 trillion years. Forget about eternity. Let's just go with another couple orders of magnitude, like 3 orders of magnitude. So multiply that all by 1,000. Well, oh my goodness, now we have a lot of time for things to metamorphosize and change their form. And maybe they used to look like that thing, but now they look like this thing. And it's just a very different way of looking at the universe, which, yeah, kind of frees the mind a little bit. So, yeah, gosh, it's hard to not talk about cosmology when you talk about anything in the sky. Okay, cool. Where are we at? Anything? Should we keep rolling? Let's keep rolling. All right, so we need to talk a tiny bit about some boring stuff regarding the numbers. I'm going to be using some different shorthand, and I want to make sure everybody's on the same page of it. Have you guys heard of scientific notation before?
Yeah.
Yeah, sort of on the same page. We'll just like point it out really quickly. So if you see a lot of these numbers that are enormous, instead of trying to write out all of the zeros after something, right? Instead of, when I see 14 billion, I don't want to have to write 9 zeros after it, right? So what do? You basically just say how many of those zeros are contained by saying 10 to that power, whatever it happens to be, right? That's scientific notation. We're going to see that over and over again. We're also going to be using SI notation, which is a little bit weird because we live in the United States. We're used to miles and so forth. We're going to be using meters and kilometers for the most part. That's the kind of international unit for astrophysics and everything we're going to be doing. So it's a pretty straightforward conversion, right? There's more than 1 kilometer in a mile. So if you want to go between the two, you want to figure out how many kilometers you went and how many miles. You basically multiply it by like a third, more or less, or sorry, 2/3. It's like 0.6. So we're all going to be European for the rest of this class, as it turns out. All right, and then another concept too, which is already cropped up, that probably is worth pointing out. We're going to start measuring things in terms of light years, which is a really weird thing to do, right? Like, why would you measure distances in terms of time? That's kind of bizarre, right? The basic idea is that if you're moving with a constant speed, well, then after some unit of time, you can back calculate how much distance you've traveled. So pretty standard logic there. It's just that the distances are so vast that it becomes preposterous to start talking about how many kilometers away even Earth is from the sun, or Pluto from the sun. It just gets ridiculous. And then we start talking about stars from one another. We would be completely lost in scientific notation, and it just wouldn't make any sense. So people mostly resort to light years. There's another thing that we'll see in astronomy, which we'll talk about when we get to it, which is the parsec, which is really just an angular distance in the sky, which is convertible to kilometers or light years. So that'll make sense. I did want to show you this. I hope this video will play. Is this the one with the video? No, we'll get there in a second. Talked about that. So light years really, really far. I got a few different conversions here, but trillions of kilometers essentially. Have you guys come across the word astronomical unit? That's one that we'll see a lot too. We should be familiar with. An astronomical unit is just how far we are from the sun, essentially. I honestly wish we could just stick with one of these and go with it, but we'll see these being interchanged, and that's just something we're gonna have to live with. I wanted to take you guys on a quick tour of the universe as far as we know it before we keep going with some of the nuts and bolts of this. I think it's good for us to at least have like a basic floor plan for this thing as far as we understand it before we get into the details of any one particular piece of it. So, our moon is really far away. So this is like a scale drawing. I think it's very hard for people to understand this, generally speaking. Everything's really far away out there. It's much further away than you probably think. You look at the moon and it looks like it's stone's throw away. It's not at all. It actually takes a few seconds for light to even really make the trip to the moon and back, right? Between your eyeball and the light reflecting off of it coming back. It's really far away. So again, when we actually start talking about something like the sun, we're talking about 150,000 kilometers. That's something like 11,500 Earth diameters between us and the sun. It's really far away. And I actually want to play you this animation because I think that I found this. Actually, my wife found this on Twitter the other day. Let me go see if I can. Oh, thought I put it in here. Goodness gracious. I'm gonna pull it up because it is worth it. See if I can just throw it up on the screen for you guys. This is pretty cool. So, turn this off. So he shows here that the speed of light is basically doing 7.5 orbits. Like if you want to visualize the speed of light, it goes around the face of the Earth 7.5 times per second, right? which is, the Earth's pretty big. I think you guys have some sense of how big the Earth is. This is the real-time speed of light traveling between the Earth and the Moon. But look how slow it is when we start looking at the speed of light from the sun as it's going towards the Earth over there. This is actually playing in real time over here. Oops, is it? You can see the little blob here moving. This is real time with everything scaled down. How slow actually light is traveling. Let's see if I can move this back a little bit. Just leaving the sun and going towards Mercury over here. It hasn't even reached. It takes 3 minutes just to get to the closest planet. Now, Mercury is like a blazing hot hellscape of a planet. It's really close to the sun by all standards compared to everything else. But look, it takes 3 minutes just for the light to get from the surface of the sun to Mercury. It's unbelievable. It takes 8 minutes for it to get to us over here at Earth, which is really wild because it means when you look up at the sun, you're actually seeing where the sun was 8 minutes ago, which is just really, really preposterous. And I guess this animation really only gets us up to our own planet. But I think that's enough to give you a sense of how bizarre this whole thing is. Oh, there it is. It's actually embedded in there after all. So I find that to be a really, really interesting piece of the puzzle here is that when we're talking about trying to study this place that we live at, everything is so far away and there's so much just nothingness in between all of these that making these conclusions often comes down to analyzing the light from these bodies alone. It will take us years to get a satellite out to the gassy giants, and so we're going to know way less than we would otherwise. All right, so we move kind of out. I mentioned Mercury. The next planet's going to be Venus. It's also quite an interesting planet. It's the only planet that's orbiting the other it's rotating ever so slightly in the backwards direction compared to the rest of the planets, which is very, very bizarre. Although it's, barely rotating, let's say. Also, a very difficult planet to live on. Really, really toxic atmosphere. A very strange planet. We move past Venus. We get out to our own planet out here, and of course, beyond us is Mars. And we're kind of the gem of the whole bunch, really. It's a very, very amazing planet we have here that looks nothing like any of the other ones we have around. When we get out to Mars, again, it's kind of a barren desert of a planet. Not a very fun place, although I hear that some people really want to move there. We'll see. Then, of course, we get past, we can see that we're actually, this part of the story that we're at right now, it's actually really close to the sun relative to everything else. You start going a little bit further past that, and eventually you're going to make your way through this asteroid belt, which will give the luxury of detail soon. And you'll find yourself at Jupiter. And Jupiter is a really magnificent planet too, because again, it makes up, a reasonable, it's very heavy, it's very large, it spins really, really fast. It has, the majority of the angular momentum in the solar system, which is another strange piece of the puzzle, given the nebular collapse formation story that we'll revisit. You keep going even further, go twice as far, you'll find yourself at Uranus. And again, go another 10 astronomical units, you'll find yourself at Neptune. Uranus and Neptune are really, really interesting class of planets. Both Jupiter, Uranus, and Neptune are ones that we see very similar types of planets all throughout the galaxy, actually. They're a very common type of planet. And it might be just because they're so big, and that's why we see so many of them. But we found a lot of these types of planets, especially the Jupiters. Like I said, the James Webb, I don't remember if this is before we started class or not, but I mentioned that the James Webb has found these pairs of Jupiters orbiting one another, quite a few of them. I think they're up in the hundreds now in the Orion Nebula, without any solar system attached to them whatsoever. So that's an interesting piece of the puzzle. The Neptunes are quite interesting. There's a type of planet that isn't in our solar system, which would generally probably be found somewhere between Earth and the Neptunes, which is called a super Earth. It's actually the most common type of planet that we find in other solar systems. So, with these fantastic telescopes, we've been able to see a number of other solar systems for the first time. Really, in the last 10, 20 years, this has become a legit stamp collecting operation. And so we don't have any of those, which is really interesting. And people have been trying to figure out why we don't have them. In fact, and we'll get into this more later when we start talking about these evolutionary ideas for the planets, but we don't have a very normal solar system at all. So when we compare our solar system, we have these Rockies, we have some weird looking planets out here. We got the gas giants, the icy giants, Jupiter, Uranus. Oops, I skipped Saturn, didn't I? Sorry about that. Right before Uranus. Most other solar systems that we see, they usually have just one type of planet, right? It's usually a bunch of these Jupiter things or a bunch of super Earths, something like that. It's also often quite ordered in terms of the size in which things, like oftentimes the big planets will be found closest to the sun. We live in this really weird mixed solar system that turns out to be the most underrepresented type that we've seen so far. So we're in a really weird place, which is also an interesting piece of the puzzle because for most of planetary science's history, all we had was our own solar system to look at. It's really only been the last 10, 15 years we've been able to see other solar systems. And I think it's been quite shocking that they don't look anything like our solar system. Yeah.
What exactly makes a planet super?
It's just a big version of Earth, basically. Yeah.
It's like rocky as well.
It's rocky. It might have a thicker atmosphere. A lot of people have started to, we'll get into all of these details later, but a lot of people have started to think of super Earths as evolved versions of Neptunes, basically. So they're Neptunes are interesting because their core is about the same size as a super Earth. And so there's different, these are still hotly contested ideas, but the idea that super Earths might evolve from something that looked more like a mini Neptune, maybe mini Neptunes evolved from something that looked more like a Neptune. Really, they start to imagine them on more of a continuum, like a metamorphic continuum. Now, of course, in order to make that happen in a really short time scale, you need sorts of massive stepwise catastrophes. You have to move the planet closer to the sun to evaporate all of its gases off and everything. So you have to do things in a hurry. Again, this is why I think it's quite interesting if the timelines keep changing on us, because you have more time for these metamorphic processes to take place, which is quite interesting. Again, the center of a Uranus or a Neptune is a great place to make a dense body because you have a tremendous amount of pressure raining down on you from this super thick, icy gas atmosphere thingy that you've got on top of you. So it's an interesting piece. It's an interesting theory, but we'll unpack that in detail. I'm going to bring the papers into that discussion. Okay, so these are our main planets. We've made it out. Pluto's 40 astronomical units. That's 4 times the distance of Saturn over here, right? It's way out there. We talked last time about whether Pluto's even a planet. Once you get beyond that, there's all sorts of little Pluto-sized objects out there. Call them trans-Neptune objects now. You also find a reservoir of comets out there, which is quite interesting. Now, people often confuse comets and asteroids. Does anybody know the difference? Oh, I wrote it on the board, so that probably ruins it. But let's just leave it at comets tend to be these kind of icy ones, whereas the asteroids are these rocky things. The comets tend to actually orbit in these really strange elliptical, really compressed elliptical orbits, which means that they visit the interior of the solar system periodically but rarely, right? And so we'll deal with comets too, because they seem to have had a huge impact on life on this planet as well. So if you get beyond the comets, you get beyond the trans-Neptune objects, you might find yourself eventually at this really interesting interface between the solar system and interstellar space. And we'll talk more next semester about interstellar space and all of that. But there's hypothesized to be a reservoir of icy bodies and asteroidy things, basically a big sea of junk out there, which is called the Oort cloud, which kind of blankets the entire solar system at its edge. Now, this is again largely inferred from the orbits of some of these comets that get displaced and come sailing in all of a sudden. But something interesting is happening there, and what's really interesting is that the Oort cloud appears to be, extend almost, let's say, at least by some estimates, 1-2 light years away from the sun, so that we can think of the edge of the solar system as being really, really, really far away. Now, if you add that to the recognition that perhaps let's say the closest star to us is maybe 4 light years away, and let's say a star that's 4 light years away also has an Oort cloud that's, 1-2 light years outside of it. It's almost like the solar systems are kind of knitted up against one another, which is a really, I think, different way of thinking about these star systems than the one that might be in our heads originally, which is that, oh, these stars are so far away from each other, they're not interacting in any way whatsoever. It may not be the case. They may actually be kind of bumping up against one another appreciably. Now, there's also this is, again, more on the astrophysics side of things, but most stars have partner stars, at least one. And this is a number that keeps going up every year too. More and more are we realizing that almost all the stars have companion stars. They orbit one another. Sometimes there's 3 or 4 of them in a bunch that are all orbiting one another. So they're very social stars. They seem to actually interact quite a bit. And there's a number of interesting puzzles in, let's say, the way that galaxies behave and move that might find solutions one day in terms of the way that the individual star systems interact in ways that we couldn't have predicted before. So, okay, this is kind of our local group of stars near us. We've got Alpha Centauri, Proxima Centauri, binary pair. We've got Barnard's star over here. There's a few within the local light year neighborhood. If we move out from that, we can start thinking about the galaxy itself. So we're all smack dab in this kind of more or less, in the interior area of the Milky Way. So you can see actually this yellow thing shows our path about the Milky Way, which is quite interesting. Most people don't think about the sun as orbiting anything. It's actually orbiting the center of the galaxy, which is really, really interesting. It takes, I think it's on the order of couple hundred million years to make an orbit all the way around the galaxy. But one thing I never realized when I first was thinking about the sun's path is that the sun's going to spend, you might think of the galaxy, it has all these arms, right? And this, this part of the course doesn't deal with galaxies too much, but needless to say, the stars are kind of bunched into these arms, right? And you might think, oh, well, the arms kind of turn as one, and the sun is kind of embedded in one of the arms, so it's moving with the arm, right? But the sun actually moves at a different speed than the arms themselves. And so the sun will spend periods over hundreds of millions of years in some of the dark regions of the galaxy, and sometimes it'll be in the more crowded areas that we associate with these arms, right, or these spurs. And so we're actually in a kind of crowded area right now, but it seems like in the past and in the future we won't be. And maybe that changes a lot of things about what happens here on Earth as well, right? There's all sorts of bizarre mysteries about our planet in terms of the larger cycles that we go through when it comes to things like the climates and the glaciations and life, huge mass extinctions, weird stuff that happens on Earth kind of periodically and predictably, but it's very difficult to map any kind of particular cycle to each of those. And so, yeah, there's a bigger orbit that we're all undergoing as this unfolds. We also kind of bob up and down. I want to play this movie too, which is maybe a cool way for you guys to visualize how this whole thing plays out. We also kind of bob up and down through the plane of the galaxy as we go. And so this will play. Yeah. Bear with me. I just want you guys to sort of visualize how this works. So I don't think that it's easy for us to imagine this orbit because it takes so very, very long. All right, here we go. This is our solar system with all of its little bodies orbiting it. There it goes. Right, and if you think about these things with actual motion applied to them, they're kind of carving out these very beautiful, beautiful helical paths behind them, right? And the whole thing is just sort of spinning its way and weaving its way through this gigantic galactic orbit over hundreds of millions of years, which is probably a more accurate way of visualizing it than just thinking about this sort of disk, this flat disk thingy. Yeah.
Several years ago, I had the luxury of attending a lecture at a planetarium where they were showing a render of this data from the Gaia project for the first time, and go kind of along these lines. One of the things they were able to demonstrate for the first time, similar to how you can accelerate time in what's it called, sky chart or whatever it is. They were able
Star Night.
to demonstrate this almost at the galaxy level. And what they were able to see was, even as these stars and orbits, as they pass each other, if we think about these interactive bodies, that you would see the gravity affect not just the star itself, but the bodies orbiting
The planets and so forth, yeah.
See some of these stars sort of shoot off, start gaining speed, velocity through the solar system.
Yeah, it's totally nuts. And it's yeah, and that it's been hard to integrate that knowledge, right? And it's been really hard for us to apply these things to some of. I think that there are ways to apply this understanding to solving some of the mysteries. We're going to come across some really weird mysteries, particularly, you know, the Earth seems to have its own cycle of motion to it. It sort of wobbles a little bit. So we talked about how the seasons are the result of the Earth being kind of tilted on its side. But it seems like, and it's basically tilted in the same direction all the time, except if you wait for a few thousand years. And then you'll find it's tilted a little bit differently. And the result of that is that Polaris, our North Star, isn't the North Star anymore, right? And so there's a cycle of a bunch of different, there's three of them really that have been the North Star over time. And, sorting out some of that information about what's going on with that, it may have some solutions lying in interactions between this solar system and whatever else happens to come passing by. It's quite an interesting set of conundrums, and there's another aspect of this too, which isn't even gravitational, which is the sun actually creates this. It's spitting out this stuff we call solar wind, which is basically just these ionized hydrogens. It's basically just evaporating this hydrogen stuff off its surface. And because it's this charged net of hydrogens, there's actually this very strong magnetic structure to the entire thing, right? So you can actually think about the solar system as having like a very real electromagnetic component to it. And this is generally termed the heliosheath, right? It's this kind of gaseous, this kind of like plasma bubble that we all exist in, right? But if all the stars have these, then they must be interacting to some degree as well. And we had this really interesting dude, this physicist at Princeton named Eric Zernstein on our show a while back. And, we were talking about all these things. Is it possible that that our solar system is kind of knitted together with the neighbor, and there's some sort of magnetic or electric processes that are at play in terms of the orbital dynamics of these things? And he's kind of like, dude, we don't know. Maybe like this is such a new revelation. We're still trying to even image our own heliosheath. We know nothing about the star next door to us, let alone the star 5 stars away or whatever, right? So these are such new pieces of information of the puzzle that the processes that could possibly be dictating, very real phenomena like climactic patterns on Earth or, the tilt of our axis over time, like there might be like totally different revelations about that possible the more that we learn even about our own heliosheath and the contributions of that, which aren't just purely gravitational. I think gravity is the easiest one to point to because it's Newton had so much success with his universal law of gravitation, and it does work really, really well in terms of defining the motion of the bodies in our solar system for the most part. But there's probably other stuff at play too. A great example is this crisis in again. I don't know how to not do this, but there's a huge problem with the galaxy itself, right? So the galaxy, it seems like what you should have happen is if gravity is dictating the shape of the galaxy, then the stars that are far away from the center should be going pretty slow, actually. And the ones that are close, just like in our solar system, should be going really fast. So Mercury flies around the sun, right? It's subject to the most gravitational tension. It's being whipped around the sun really fast. And then you move away and like everybody kind of goes slower and slower and slower and slower. The galaxy is not like that though. It's really weird and nobody knows why. So the galaxy kind of moves as if it's one homogeneous body, more or less. Like I said, individual star systems might go slower or faster, but on balance, it kind of has a homogeneity to it, which is really, really perplexing. And so people have proposed all of these really exotic answers, like there's this invisible form of matter called dark matter that knits it all together. Maybe, but there may be also processes at play in terms of literally stitching one solar system to the next that might have a piece of this puzzle to offer as well. And I just don't think that we're there, even in terms of the observations yet, to really know how all of that works. So what do you guys think? Questions? Concerns? All right. Let's keep cruising then. So, I want to wrap up this piece by just kind of giving you guys a sense of just how unbelievably large this thing is. So we can move. This is our local groups. This is our galaxy down here, right? There's some little satellite galaxies over here that are kind of like grouped right around us. But then to go out and actually find another galaxy, you need to basically go something like 4 million light years to find a neighboring galaxy. 4 million years of light's travel path before it can even reach that neighboring galaxy, right? Then you start to move further from that, and you start to find that the galaxies in general are all kind of organized on these strings, which is really crazy. They call this web the cosmic filaments or the galactic filaments, right? So there's really widespread organizations of even these things which are impossibly far away from one another. And again, how are they doing this, right? Is it purely gravitational? Are there streams of ionized material that are stitching these things together? Nobody knows, but it's a really, really cool aspect of this entire mystery, which is that the organizational structures don't seem to get less complex the further that you zoom out. They actually seem to get more complex. I mean, let me give you another picture of this thing. So this is I think this is more of an artist's representation of these galactic filaments, but we're talking about, hundreds and hundreds of millions of light years long for each one of these little threads of galaxies. And each one of these threads is made out of, maybe dozens, maybe hundreds of different galaxies itself, right? So there's just an unbelievable degree of organization of all of this material from, our solar system to the sun providing this heliosheath, which is structured to the individual interactions between suns to the galaxies interacting with each other and creating these widespread structures. It's incredible the degree of complexity that emerges at each scale. So that's essentially the universe as far as the best of the astronomical minds can make sense of it at the moment. Not that that's much of an explanation, but it is a little bit of a tour of where we're going. And when we get back and start looking individually at each one of the bodies, we're going to stop at the solar system. But I wanted to kind of preview what's out there beyond it as well. And of course, next semester, we'll be dealing with galaxies and stars and how they work and all the weird types of stars and why we think what we think about them. Questions, thoughts? Yeah.
Just clarifying, we're talking about them separately. They're obviously separate entities or whatever, but the distance between the Oort cloud and the heliosheath. I'm curious where the heliosheath rests in referencing the
Yeah, that's actually a really good question. Can somebody Google where which one comes first? I don't actually know the answer to that off the top of my head. Does anybody have like a Google open or something or a chat bot? Somebody got a computer? Yeah, ask where's the helio sheath with respect to the Oort cloud? Um, I want to say that it's before the Oort cloud. I could be wrong about that though. Then again, that doesn't totally make sense to me either. Let's find out. It's a really good question. Um, that what's really interesting about the helio sheath too is that it seems to have like it's sort of lopsided. It's kind of like a teardrop. Like the back of it extends out almost like a comet behind us, and then where the sun is actually making its orbit around the galaxy, it's kind of colliding with the interstellar medium. So you get this kind of shock wave as it moves through. You guys got an answer?
I like the Google AI.
Yeah.
It says that the Helios sheet is located like within the Oort cloud.
Okay, that's right there with it.
Closer, but it says it's much closer to the sun.
Okay.
So I think
On the interior of the Oort cloud. Interesting. Yeah, still, I mean, nobody's ever taken a picture of the Oort cloud, so it's in some sense a hypothetical entity. It has crossed that. I think it's crossed the heliopause, right? So it's broken through that shockwave. Yeah, that's a really interesting piece of the puzzle too. That's the gift that keeps on giving Voyager. It just seems to. They thought it was going to die a long time ago, but it just keeps phoning home. And yeah, I think it's really interesting to see what we learn. But it turns out that interstellar space is not empty or boring at all. There's a lot of activity out there, and I think this interaction between what's out there as the solar system collides with it is, in some sense, what gives shape to this entity that we're calling the helio sheath. It's really just this interface between the sun, which is basically a fire hose, and all of that static medium, really a lot of gases, neutral gases, ionized gases, just stuff out there in interstellar space that it's colliding with. Um, but yeah, in terms of how all of that organizes to knit things together and get these wider structures, I think those are questions that probably have answers we just haven't gotten to yet. I think they're pretty cool mysteries. All right, what else? Anything? Yeah.
Lies with interstellar space does not pick up a lot of stuff that becomes part of us.
I mean, that's a really interesting question. That's a huge question. I mean, um, it's very so. One of the troubles with those kinds of theories is that uh, it's one of the objections to the kind of theories that the solar system would incorporate new bodies into it is that it's very difficult to stabilize the orbit. However, it's not impossible. So there's an astrophysicist I know at the University of Bordeaux. Oh God, his name is slipping my mind right now. But he does these really cool simulations where he'll try stuff like that. And he basically runs a computer game for a living. Like he can try, well, how close would a star have to pass with what planets and what alignment in order to actually have it get scooped up into an orbit, and then in order to have it be stable into an orbit that would, you know, end up. And it's like his conclusion's kind of like, yeah, it can be done. Um, Most of the time it's a disaster. Like most of the time it just rearranges all the orbits in the solar system. Somebody gets kicked out. Um, or like somebody goes tumbling into the sun. Like it's most of the experiments don't work out. But I don't think that the rareness of things happening is necessarily a reason to discount them wholesale either. I mean, it seems completely rare that a bunch of atoms would assemble themselves into human beings and be sitting here in this lecture hall right now. But it is happened. It might be extraordinarily rare, but it certainly has happened. So, yeah.
Was it called Universe Animals? Was that what was using?
I know that one. Yeah, no, I think he was. I think he's built some of his own simulation software for his, for these academic projects. But I do know that one. That one's cool too. I've seen some really cool videos that people use that to try out different scenarios. But yeah, something very similar, I think. But perhaps with like a little more parameter space in terms of whatever the heck he wants to input into these systems. It was just cool to like try on some of these scenarios because I think that a lot of these ideas don't get a lot of play because they're just discounted as being rare. Like, well, it's very unlikely that that would have happened. And it's like, well, okay, like might be though. Might be very rare, but very possible. So yeah, I don't know. Maybe we do have encounters with other solar systems. I mean, a really good outstanding question is like, where the heck is our partner star? That's weird. I mean, yeah,
I've heard a theory once that Jupiter would have that there was something that prevented Jupiter from being a partner star because in other solar systems that don't have partner stars, they also have something like akin to Jupiter, a gas giant or a brown dwarf or something similar of similar mass.
yeah,
Didn't quite reach.
yeah, yeah. Yeah, I think there's a reasonable case to be made that the difference between a Jupiter-like planet and a star is not that much. It's just a matter of atoms, actually. I really get into this next semester, again, because we're dealing with stars, but look, Jupiter and the sun are basically made out of the same stuff in more or less the same proportions. Jupiter's just not that big. You get a bigger version of Jupiter, it's called a brown dwarf, right? Brown dwarfs do actually fuse material like a star, they just don't fuse neutral hydrogen, right? They're going to fuse heavy hydrogen. Um, and so they're kind of like stars, brown dwarfs, and they're kind of like Jupiters, but again, they're bigger. But at some point, you get enough hydrogen or helium crammed onto a brown dwarf, and it's a star. And so a fun thought experiment is like, what's the difference between a brown dwarf and an actual star that's in glow mode, where it's actually fusing hydrogen and giving off light? It's like, so what's the difference between a brown dwarf and a red dwarf? It's like one atom. There's like one, at some point there's a straw that breaks the camel's back, right? You get enough material in one place, then you have the pressure to actually pull off that task of being a star. And so it seems like, following from that thought experiment, it seems logical that there's probably some stars that spend some portion of their lifetime looking like stars, and then maybe they lose that atom, and now they're a brown dwarf, they're not glowing anymore, right? So maybe the thing could work both ways, I guess is the way that I'm looking at this. Maybe some of these bodies that we see are used to be stars, maybe some of them are failed stars. Maybe some of them never had a chance of becoming stars. There's a really interesting survey that was done, actually accidentally, by the US military, where they were, I think, looking out for like Russian spy satellites over the course of like the 50s through the 80s or something. And they made these repeated photographs of the night sky in certain sectors. And some scientists got a hold of all this data many years later, particularly a Spanish scientist, I believe she's Spanish, I forget what university she's at, her name is Villarroel. And she put together this huge analysis, and she found something really crazy, which was that a lot of things that you would probably call stars disappeared. Like, they just completely disappeared. And of course, she did what a good scientist would do, and she tried to talk herself out of it. So she was like, okay, maybe this one was an artifact on the camera lens, or maybe, you know, maybe like the sensor wasn't working that day. Like, she was able to rule out some of it on that basis, but she was still left with like hundreds of these apparent stars that just seemed to go dim over the course of 30 years, which is just completely shocking. Like, nobody thinks that stars are going dim every 30 years. The standard story that we tell for the lives and deaths of stars is generally quite violent. But that data is in some sense standing in stark contrast to that conclusion. So she's a very, very careful scientist, and she's very afraid of the conclusions that she's making, that she's made from this, because I think they're quite heretical. But there might be a more mundane way in which stars kind of just get tired and become something less than a star. Again, fringe perspective, yeah. No, go for it.
Like that, like when they make the star.
Yeah.
And they have like our human bodies or like a hard object in the chair. They're like sort of compounded like differently.
Yeah.
And then so like the process of like so atoms being compounded differently to like make a star and a human. Like they run out of energy or whatever, and then like a star dies, human dies. But what like is there a difference between like a hard compound of atoms and then the atoms that like
make our body restore.
Yeah, there is. Yeah, I mean, the biggest difference is like condensed matter versus gaseous matter, essentially. Um, so you know, and but of course, it has to do very much with how the atoms are knitted together, right? So basic idea on one end of the spectrum is that some atoms are just sort of free floating; they're not compounded, as you would say, and we call them gases, right? And then we have condensed matter, like the desk, like this water that I've been drinking, which is essentially all bound. It's all tied up to each other, right? You can have liquids that are condensed. They have more fluidity. They can still change. They're not married to their position in that lattice, but they still have a lattice. There's still actually a real, like if you, and there's ways to study that even with liquids. You can actually see that they do actually have some structure to them. And then on the gaseous end, you get into some weird states too when things get really hot and depressurized, which is where we get into this word plasma, which is a real nightmare, but we'll give it its due diligence next semester. It's too big of a concept to do right now. But plasma kind of, that word sort of hides a lot of misunderstandings, or mysteries, I prefer to think of it that way. Because oftentimes we can say, oh yeah, well, it's just a plasma. And it's like, well, what is that? What are we actually talking about here? What are the atoms actually doing? Is it a liquid-like plasma or is it a gaseous-like plasma? Because they're going to have very different properties. And oftentimes it just gets rolled into that word, which is why the sun is hiding quite a few mysteries still, as far as I can tell. Because the question of whether the sun has condensed matter as its basis or not, regardless of whether it's the fact that it's considered a plasma, those are two very different sets of conclusions that result from whether you conclude that the stars are condensed or gaseous. You end up with very different stories for their lives and deaths depending on how you see it. So that's pretty much at the core of everything we're doing next semester, because you end up with two very different astrophysics depending on the condensed versus uncondensed version of these bodies. It gets very, very interesting.
The atoms themselves. Yeah.
Yeah, the compounds. Oh, that's a good question. Yeah, I mean, so atoms do decay. Yeah, atoms do decay, and they also can reform, right? So I often kind of think of them as like blebbing off from one another. This is sort of what the fission process is. You heard about like nuclear power, nuclear bombs and stuff. It's really atoms that are breaking apart into new atoms. The same thing can happen in reverse, but it takes a tremendous amount of pressure to pull that off, which is why we generally think of atoms only being formed inside of stars or during like huge explosive processes. There may be more to that story too, but I'm afraid we can't dwell on the stars as much as I would love to. Although I do think they are the absolute linchpin of everything. For whatever reason, this course has been organized before I got here into planets first, stars later. Although every year I teach this, I think, man, we really should start with the stars. Yeah, but here we are. Okay, let's make it through a couple of more important sort of nitty-gritty pieces of this. You guys got through some of this in textbooks, so I won't belabor it, but I want to make sure that we understand the basic floor plan by which, people have started to chop up the sky, which, it will prove somewhat important in terms of orienting ourselves to the different bodies as we go through. This is the modern system, right? So does anybody have a telescope, by the way? Nice. Couple of guys? Anybody else? Yeah. So when you set up a telescope, you have to be kind of keenly aware of this. You have to sort of adjust the axes and stuff so that they correspond to this concept of the celestial sphere. Now does anybody remember anything about what this celestial sphere thingy is all about? Does anybody remember? You guys probably came across this. Yeah.
Well, the textbook is basically just the sky. It's just the idea of the sky. It looks like a sphere that's moving around the Earth.
Yeah, that's the way most people thought of it for most of time, right? And it's totally accurate. Like, there definitely is a sphere of stuff moving over your head. Like, from a very relativistic standpoint, that's what it looks like. That's what happens every night. And that's the way that people set up their astronomical measures for most of time. And we've kind of stuck with it. So we basically treat the sky like it is a sphere that's moving over our head, even though it's equally valid to say that sky is there, and we're actually the ones that are spinning around, and so it just looks like there's a sphere overhead. They're both kind of true. Just depends which vantage point you're at. So we call this thing, this bubble that's all around us, the night sky. We call it the celestial sphere. And the whole thing sort of rotates about the north-south axis because, of course, the Earth is rotating inside of this sky about the north-south axis. And so one thing that's really convenient about that is that if you can identify where that pole is, that north-south axis, you can actually get a pretty good sense of where you are on the planet, which is actually one of the probably earliest reasons why people, especially people navigating by ships, but probably by land as well, it's very nice to know how far north or south you are. So it's kind of a cool feature of this, right? If you go out and look at the night sky, maybe make a time-lapse photograph of the night sky, you'll see something like this, depending on whether you're at the northern hemisphere or southern hemisphere. It doesn't matter. You could look to the south if you're in the southern hemisphere. Up here, we look to the north. And if you focus your camera on the North Pole, you'll see that the sky tends to sort of rotate about it. Now, this is really cool because the further that you get towards that North Pole, what happens to elevation at that point? Where does that little center of the swirl end up? Yeah, it ends up right above you, right? If you're at the North Pole, you look up and that's what's happening, right? So the cool thing about that is that the further you move away from the North Pole, the more this thing sinks down to the horizon, right? And that is the concept of latitude, right? You guys have probably heard, like, what latitude are you at? That's literally what it means, is how many degrees is that pole star above the horizon for you? I think down here in Ashland, it's something like 42 degrees or something like that. And when we say degrees, what do we mean? We just mean we've chopped up that 180-degree arc above our head into 180 degrees. Degrees is a weird unit of measurement, by the way. Maybe I'll come back to that some other time. It's very, very bizarre. It's one of the only places we don't do the decimal system with. We inherited this from the Sumerians for some reason. We do it with time, too. It's very, very bizarre. Okay, so this is the basic unit by which you can apprehend your latitude. So here's just the schematic representation. This is in your textbook, too. But, you're going to see something very strange. So what does it look like if you're at the equator? What do you have? Yeah, you probably have one on either side, right? You can see the north one over right up, just literally sitting on the horizon, right? At like right on the horizon, and then you have the southern pole star also, the southern celestial pole down there. So you have two swirls on either side, which is really cool. I've never actually seen it. I have been to the equator, but I didn't know to look. So yeah, you basically see something like this in either direction, whichever way you look. So yeah, you can actually calculate your latitude, which is really cool. And I think it would have mattered a lot to people who were trying to navigate and stay in the shortest path between 2 points, especially at sea. People were really good at navigating by sea several thousand years ago. Like the height of maritime navigation, most people don't know this, the time when people were navigating the most and most efficiently and they had the widest maritime trade network set up was actually like 1500 BC, which is really weird. They didn't actually get good at sailing again, as good as they were in 1500 BC in the Mediterranean. They didn't get good at it until almost this sort of a colonial period of expansion in like the 1700s, right? So that's pretty bizarre that for 2,000 years there was kind of this dark age of navigation. But the point is that people were really good at navigating prior to anything looking like GPS or any real sensible picture of even the fact that we're sitting on a sphere in the first place. But they did probably have some knowledge of where the stars would point them in terms of where they were at latitude-wise. Longitude turns out to be a whole other nightmare. It actually requires that you have some timekeeping system because you need to gauge how far east or west you've gone, and that didn't appear until much, much later. So that's pretty cool. You can actually measure these degrees. So if you want to know your latitude, right, a degree is more or less something along the lines of the size of your pinky if you hold it out at arm's length. And so if you look up at the sky. And there's a couple other measures here too. So 5 degrees is like 3 fingers, knuckles, 10 degrees, 15, 25 degrees. So what does all this mean? It's like if you do this with the moon, you can also see that the moon's about a half a degree in angular measurement. That's what we would call it, I guess. And this is pretty cool because you can actually measure your own latitude just using your hands if you want to. Be like, what, 4 knuckles where we're sitting right now? 4 stacked fists above the horizon. Of course, you need to probably make some measurements because you need to see what points, or you need to know where the North Star is. And I think that that's what I would like to lead up to at this point. I'm going to skip that. This was that podcast, by the way, if you guys are interested in the helio sheath discussion. It's from a couple years ago, but it was a really good conversation. So yeah, finding the North Star. The North Star is actually, it turns out to be one of the central features. I feel like it appears in more mythos than anything else, and I wonder in some sense if it has to do with its importance in navigation. You guys have seen this painting before, right? You guys notice the dipper in the back there, the Big Dipper? I never really noticed it before until somebody pointed it out to me. The dippers are actually the way in which we can locate that point upon which everything is circling. So you can go out at nights and you would have to sit there for a really long time to actually see the point upon which all of the stars are rotating, right? But if you can identify the dipper, then the dipper actually points towards where that pole star is, right? Which is actually kind of in the tail of the Little Dipper, or the Little Bear, as it turns out. So if you can find those points, then you basically know where the North Star is, which you'll need if you ever use a telescope, because you kind of have to calibrate it so that it'll spin properly as the night sky turns. And once you have that pole star, then you can basically figure out where you are in terms of the north-south axis, which is really cool. It also turns out to form the bedrock for a number of different mythos which appear all across the world. And I think I'm going to save that story for a moment, but I think that it's a story worth telling because the story that has been associated with these dippers, it has a tradition in the West. We actually refer to them as Ursa Major and Ursa Minor, which is this bear. But it's a story that's told all over the globe. And in many places, they use different creatures and animals to tell this story. But the stories are actually quite similar to one another. And what's even more bizarre is that many tribes in North America, particularly around the Great Lakes and on the East Coast, also tell a story about bears and hunters that are associated with this. It's not a constellation, it's a sub-constellation called an asterism, but with the dippers. And so I want to kind of compare those stories and see if we can understand what the heck they were getting on about and why this is so important to everybody. Anybody have any final questions before I let you guys digest some of this for the weekend? Yes. Hey, Sarah.
With all of the constellations that have like similar stories, and you saying that there used to be like heavy navigation back in prehistory,
Yes.
like the thought that maybe we were communicating and we weren't globalized, and then that.
Yeah, I want to go there next. I'm going to go there on Tuesday. It's a absolutely crazy situation. So we'll look at it in depth. You need more than mythology to make that kind of a claim, but there's some really interesting features that I want to talk about. There's also there's the possibility of dispersion, common ancestry, like shared culture very deep in the past. There's many reasons, but I want to look at those myths and compare them to each other. So we'll start there on Tuesday before we get back to the physicsy stuff. Cool? All right, have a great weekend, guys. We'll do it again next week.